Hello, my name is Elizabeth Myers and I'm a physics teacher at Central High School. In today's video, I'm going to be talking about rainbows and sundogs because they're an example of refraction in the sky. And they can tell us a lot about what's going on in the sky, specifically the weather. Today's slideshow will focus on refraction, and an example of this is rainbows. And this comes from the state standard 9P4111, evaluate the claims, evidence, and reasoning behind the argument that electromagnetic radiation, aka light, can be described using either by a wave model, and refraction is an example of that, or a particle model, and that for some phenomena, one model is more useful than the other. So what happens to the speed of light when it travels from one medium to another? In figure 1a, we have a glass block, and as light leaves the glass block, we're expecting it to travel straight. But as you can see, just at this boundary point, it actually bends. And so our perception of having the light travel in a straight line makes us think that the block is actually thinner than it really is. Another example of this is looking at a fish in water. When we expect the light to travel in a straight line, we would expect the fish to be where that sort of pale outlined fish is. But in reality, light changes direction when it leaves the water and goes into our eyes. So the fish is actually deeper than expected. And finally, in figure C, it appears as though there's more coffee in this cup than there really is. And that's because when the coffee leaves the light leaves the coffee and goes into the glass, and then leaves the glass and goes in the air, it actually changes direction, appearing as though the glass is quite thin and is mostly coffee. So what is the cause of this light bending? It's refraction. Refraction is light changing direction, and this occurs when, in our figure 2, you can see light traveling through water, and then as it hit this boundary between water and air, it changes direction. So refraction occurs when light hits that surface at a non-90-degree angle. So here I have an ordinary pencil and a glass beaker. As I add water to it, you can see the water filling up the beaker, and somehow this changes the overall appearance of the pencil. If it hit along this dotted line, there would be no refraction. In addition, light needs to change speed when it crosses a boundary. Here we have a large Pyrex beaker, and I'm putting a smaller Pyrex beaker inside of it, and then a test tube inside of that. I'm going to pour baby oil in between the two beakers. And at first, it doesn't really seem that different than normal. But you can start to see the edges of the small beaker blur, and the test tube at the bottom is very clear as you look through the beakers. Now when I start to add oil inside the smaller beaker, then the smaller beaker starts to disappear. And the reason for that is that light doesn't refract when the medium has the same speed. And light travels the same speed in baby oil as it does Pyrex, but not the test tube. So you can see the test tube just comes right out. It's not magic. It's just refraction. Well, actually, it's not refracting. As you can see, these two rays are not actually parallel to each other. There is a change in direction that occurs at the boundary. Now, we can make some predictions based upon the speeds and angles to know which way the light will actually bend or refract. So in this example, we have Snell's law written with the velocities in air multiplied by the sine of angle in water equals the velocity of the light wave in water times the sine of the angle in air. So we would measure the angle in water from the ray to that perpendicular boundary called the normal. And then we would measure the angle of the ray from the normal, that perpendicular line, to the ray of the air, and insert that in our equation. One of the labs that I would have students do to practice calculating speed or angle in refraction would be using the simulation from PhET, Physics, Education, and Technology. And so this interactive is available on their website. And on the right-hand side is an example of one of the labs that I would have students do. So first off, you can see we have air on the top and water on the bottom. So when you turn on the laser, you can see that the light is reflected in air, but also it is refracted, and students have the opportunity to measure that with the protractor. Now they can change the speed, and that's shown as the material, because that material has different speeds inside of it, and so then they can measure the angle also. Now you can change it completely, having water on top and air on the bottom, and you can see the angles are different. So this gives students an opportunity to practice using Snell's law, measuring angle, and then calculating velocity, or maybe measuring velocity and calculating angle. Next up, we have individual prisms. So here we have a laser hitting a triangle, and then they can rotate the triangle and see how the angle changes. They can also do multiple lasers or white light. And so you can see that it's very hard to see here, but down on the lower right hand side, you can see all of the colors of the rainbow. And again, they can play with the angle. Now we can try out a convex lens. And when the ray hits it straight on, there is no refraction. So there has to be a non-perpendicular angle in order for you to see that bend. So this is a concave lens. This is a lens more common for people who are nearsighted, and you can see the rays diverge or send apart. And then they do have a perfect circle, which is more similar to a raindrop. Again, you can see the refraction there, but it's not super big at the front, but you can see it more clearly at the back. So this is just an example of what I would have my students do in order to practice calculating angle and measuring or measuring the angle. Now, white light is the overlapping of all the colors. And in the figure 3, white light is shown as black. But when the white light hits this boundary, the light actually has a change in direction. And you can see both red and blue, and actually all the colors in between red and blue. The reason for this is each color interacts with the molecules of glass differently, which causes each color to travel different speeds. Having a different speed means that each color bends at a different angle. Blue travels the slowest in glass, so it has the biggest change in direction. A rainbow is caused by when you are looking at raindrops in the sky and the sun is shining behind you. In figure 4, you can see sunlight, again shown as black, which is supposed to be white light. When it enters the drop, the light rays refract, again traveling at a different angle because they travel at different speeds. Now the light rays reflect, meaning bounce off the back of the drop, and then they refract again as they leave. Notice here there is quite a separation between red and violet, again imagining that all the colors in between would occur there. Now, each drop doesn't send you a full rainbow, even though each drop does send out all the colors. You see a rainbow by observing colors coming from different raindrops. So in figure 5, we see just 2 raindrops shown, where the top raindrop gives us red and the bottom raindrop gives us violet. The rainbow's position is dependent on the position of the observer. So if the observer moved up here, they would see the violet coming from this top raindrop, and that would make the rainbow move in the sky. And that means everyone will see the rainbow in a different position in the sky. Now in figure 6, we have a person drawn here as the center of the rainbow. And that's true because directly behind them is the sun, and directly in front of them is the anti-sun or anti-solar point. Now the rainbows are actually circles, it's just that there's no raindrops below ground, so you don't see the full circle. Now the math of this is based upon how much the speed changes of the different colors in the raindrops. And so we see again that the red is 42 degrees from this sort of axis of the sun to anti-solar point, and the violet or purple is 40 degrees. You can actually measure this with your fists, so from the center out to The purple is about 4/5, sorry, 4/5 hand fists. Now we can predict the location of the sun knowing that our antisolar point is opposite of the sun. At noon, the sun is at its highest, and this would make the antisolar point in the ground, so you can't see a rainbow at noon. However, the higher the sun, the lower or slash smaller the rainbow, because it starts to get tilted downward. If we had the opposite later in the day, then it would be tilted up. At the very last moment, if the sun is already set, due to the fact that we have a curved earth and there's a refraction of light through the air molecules, you actually see a slightly larger than a circle. You see more of a semicircle than you would expect, and this is because the sun is actually set behind you. Now, there is some lore about, weather predictions that can be made based upon the rainbow. So if you see a rainbow in the morning, since we get our weather from the west, this means that a rain shower is coming because the raindrops are coming towards you. If the rainbow is in the evening, this means the rain has already passed, and so you're going to be looking at a clear sky. Some weather lore is a rainbow at night, fair weather in sight, a rainbow at morn, fair weather all gorn. So the intensity of the colors of the rainbow can tell us a bit about the droplet size. So as the droplet size decreases, diffraction effects cause the color intensities to weaken. So that means that when the droplet size decreases, the colors that come out of the droplets overlap each other and they cancel each other out, producing white light. So if the droplets are big, all the colors are bright and clear. If the drops are medium sized, then the red band is visible but pale. And then again, if all the drops are small, then all the colors appear very pale. So a little bit of old weather lore, lots of red means a wet head. Now what happens if we have very small droplets of water suspended in the air? Well, that could mean fog. And with these very small droplets, we produce what is called a fog bow. Now notice it doesn't actually have any colors, and that's because, again, the droplets are small, so those colors overlap each other, and all the colors together would make white light. So we do have I wouldn't say an intense band of light, but it's more medium to pale, but you can definitely see that fog bow. Now what happens when it's cold out and we have precipitation or crystals in the air? So this is a picture taken outside of my high school on February of 2023, and you can see the sun in the middle, and then what looks to be two suns on either side. These are called sundogs, and they're false suns. They're obviously not a real sun. So what causes sundogs? They're caused by a high sun angle and cold temperatures. You can see the snow on the ground, so it's definitely cold out. And the refraction of the sunlight through ice crystals in the air, in this case, usually high cirrus clouds. What this could indicate is this warns, not warms, warns of an advancing front and possibly precipitation. So thank you very much for listening to me talk about refraction and its examples in the atmosphere like rainbows, fog bows, and sundogs.